we have a GitHub repo with 3 notebooks. Leandro just presented the transformers tour, and we're now going to have a look at the text classification example. So I'm going to chuck this in the chat. Oh, maybe Leandro, oh, here we go. I can do it here. And if you look at this this notebook, there's a little open in Colab button. And if you click on that, it will then open up a notebook for you in Colab. And yeah, Colab gives us free GPUs. So you can click on runtime, and then you can go to change runtime type. And you just need to make sure that you've got the GPU selected here, because we're going to need that for what we're doing right now. And if you have any troubles, just post your questions in the chat, and Leandro or Nina can help you. Okay, so Leandro has shown us how to do inference, basically. So we've looked at using a pipeline in transformers and all the different tasks that we can use the pipelines for. And I think this is a great way you can sort of bootstrap your projects. Most of the time when I was working in industry, it was using the pipeline was just a way of getting a feel for like which models might be good candidates for the task I'm interested in. But eventually you'll reach a point where you need to do the fine tuning yourself. And that's usually because you're working with your own data, and that data could have, for example, a different number of labels to the existing models. It might be domain specific. So maybe there is like some vocabulary or language in the data that is like relevant to your business or your task. And, you know, these kind of generic models that you can get from the pipeline maybe aren't up to scratch. So what we're going to have a look at in this notebook is how to do the fine tuning process. And then in the second notebook, we're going to look at how we can interact and create a demo of this model on the Huggingface hub. So since we're in Switzerland, we're in a multilingual setting. So we've got German, French, Italian, Romansh, and maybe English is, you know, soon going to be a national language. And Swiss German, of course, which is a much harder language to model than the others. So what I thought we could do is we could look at a multilingual application where we're going to take a data set which is provided in multiple languages, and we're going to fine tune a transformer on one of these languages, and then we're going to evaluate how well it's able to generalize to the others. And the main thing that we will cover is essentially how to load and process data with Huggingface library, and how to create a baseline with the zero-shot classification pipeline that Leandro showed us, and also how we can evaluate the model and compute metrics and things like this. So the usual thing you'll need to do is just install the dependencies. So Leandro just talked about transformers and sentence piece, which is for tokenization. There's one more library we're adding here called Datasets. And this is a library from Huggingface, which provides very memory efficient computations or processing techniques to analyze text data, and also soon vision data. And the other thing that you'll need once you've created your account on the Huggingface hub is to log in into Colab. And so what this will do is this will, if you run this cell, it will give you this kind of widget, and you can put your username and password from the Huggingface account. And then this will generate a token that we can then use to automatically push the models we train to our account on the hub. So you'll want to run that. And then there's one last thing that you need to install to get started, which is called Git LFS, or Git large file storage. And so one thing that we use at Huggingface for all of the models, the data sets on the hub, is basically Git on steroids. So Git LFS allows you to do version control using the standard Git interface, but for things that can be, you know, gigabytes or maybe even terabytes. So you just need to make sure you've got that installed. And with that, we can get started. So throughout this notebook, I've injected a couple of videos from the Huggingface course, which just give you some additional context of what we're talking about. So if something I say right now isn't immediately clear, or you'd like to dive deeper, you can just watch these videos, or you can check out the course itself, which provides a lot of additional context. So the first thing we want to do is find a data set and play with it. So the one that I've picked is called the multilingual Amazon review corpus. So if we look at this data set on the Huggingface Hub, you can see that it's got like a description in a dataset card, and we're told that we've got Amazon product reviews for text classification in English, Japanese, German, French, Chinese, and Spanish. So this is like a nice starting point for, say, the Swiss context, because we've got German, French, and English. At least these are like some of the more prominent languages. And we're also told that each record has some review text, a title, and a star rating, plus some additional metadata. So this is a fairly popular data set for benchmarking text classification models. And so, yeah, let's see how we can, first of all, download this model from the hub. So the data
just quickly,
yeah.
Can you maybe mention what the things on top mean on the hub? Yeah.
Oh, great. Yeah. So when we're looking, when you're trying to, for example, search for data sets or models in the hub, you'll have a couple of filters that you can use on the left-hand side. So you can see here we've got some task categories. We've got the actual sort of subtasks, the specific tasks, the languages, whether it's a multilingual or monolingual data set, how many examples are in the data set, and what kind of license is provided by it. So this is handy if you're, for example, interested in the 3,800 data sets down to 300. And then we might be specifically interested in, say, multi-class classification. And then we might say, okay, maybe we want something that's maybe multilingual. And okay, in this case, the tag didn't give us what, the Amazon reviews, but, maybe if we pick something like Spanish, then, okay, we're still missing something. So the tags don't always give you the exact thing that you're looking for, but this is a great way to get started. And you can see already when we just picked text classification in Spanish that it's already up here. Okay, so the datasets library has the main function that you need to get started to load datasets is obviously called load dataset. And this function receives two main inputs. So one is the name of the dataset on the hub. And the second is that the dataset might have multiple configurations or subsets. So for example, in the case of the Amazon reviews, we know that there are different languages. And so these are provided as individual subsets that you can access instead of having to download the whole corpus. And so one way you can see what kind of like subsets are available in your dataset is to use this function called getDatasetConfigNames. And when you feed in the name of your dataset, which in this case is Amazon Reviews Multi, it will provide the list of available configurations. And so you can see here that we've got German, English, Spanish, French, Japanese, and Chinese. But you can also download all of the languages in one chunk if you're interested. So what I thought we could do is we could take German as a starting point. So here I'm just loading the dataset with the dataset name, and the specific subset is D. And you can see it's doing something very similar to what we saw with the pipeline, where it's downloading lots of different components in different steps. And all of these files will be stored also in the cache of your computer. And the cache in this case will be at Hugging Face and datasets. So all of the models will go to Hugging Face models, and all of the datasets go to Hugging Face datasets. And the great thing about this is that once you've downloaded the dataset once, if you kind of, turn off your laptop or kill your notebook, it will keep those datasets stored in your hard drive, so that then when you reload in a second session, it will just load them from the cache instead of having to download them again from the hub. And this gives you much greater speed, usually if your internet is not super fast. So when you download the dataset, it will return usually something called a dataset dict. And this is kind of like a Python dictionary, which has keys and values. And the keys will refer to the splits that the dataset provides. And the values are these other objects called dataset objects, which are kind of like containers that we can index into, we can compute the length of, we can do transformations on. And so what you can see in this example is that we've got 3 splits. We've got a train split, a validation split, and a test split. And each of these data sets has some number of rows. So we've got 200,000 reviews in the train set, 5,000 in the validation and test sets. And we've also got some number of columns, which are basically going to be the features that we're going to use to build, to train a model. So let's have a sort of inspection of one of these splits so that we can kind of understand a little bit what's happening under the hood. So the dataset dict object I created was the Amazon reviews, what's called the multi-Amazon review lingual corpus, so I call it Mark. And if we just select the train split, then what we get is a dataset object, like I was saying before. And this dataset object, we can query various things about it. So we can ask, for example, what is its length? And this is maybe familiar if you're used to working with Pandas or NumPy. It's got very similar familiarity. It's like a similar kind of API of like, you can index things, you can slice, you can do all this kind of stuff. And so here we've got 200,000 reviews. And if we just select the first element in this data set, then what you can see is that the representation of each row is actually a dictionary. So we've got here the name of the column and then the value. And then we've also got, the product category. We've got the number of stars that review had. And we can see here in the review title that it seems like, unfortunately it was broken after 1 year. And what was broken specifically was some armband. And so the thing that we're going to do is we're going to feed the review body to our model, and we're going to use it to try to predict the number of stars. So then in the future, we could, provide new reviews and just try to see what kind of essentially sentiment is associated with these reviews. And by the way, please, ask questions in the chat if I'm going too fast or something doesn't make sense. Okay, so the other thing that the dataset object has is column names, very similar to Pandas. So we can see here we've got these different column names, and we can also slice this object in the same way we do with NumPy or Pandas data frames. And so here you can see that the difference from just looking at a single row versus a slice of rows is that we still have the key for the column name, but now instead of having a single entry, we've now got a list of entries. And the reason this happens in datasets is that it's based on a very powerful framework called Apache Arrow. And Apache Arrow is a way of creating data structures that are extremely efficient for data processing, but are also slightly different in flavor to what you might be familiar with say, Pandas. So in Arrow, everything is like a typed columnar format, which means that instead of doing all your operations kind of row-wise, you typically try to do them column-wise. It's much faster to do these things this way. And they're also typed, which means that if you're used to using Python, you probably know that like you don't really have types that you can fix the types of your objects. They can kind of freely be overridden. But Apache Arrow is very strict about what these types should be. And so you can look at the types by accessing the features attribute. And here you can see that, for example, the language column is a value type of type string, whereas the stars column is a type integer 32. And this is what allows Apache Arrow to process data very fast, because you don't have the sort of limitations that you get with normal Python. And Datasets, the library, is based on top of this Apache Arrow framework. But we don't really need to know about that in detail. Today, we just need to know how to use the library. But if you're interested, that's what's going on. So one thing that usually happens when you're doing any sort of data analysis, especially in NLP or with tabular data, is you're probably used to using Pandas, the library. And Pandas for me is like a great library because it gives you lots of flexibility with doing aggregations and filtering and stuff like this. And when the Datasets library was designed, it was designed to be interoperable across many different frameworks. So you can actually change the format of your data from this Apache Arrow, which we talked about, to Pandas data frames, to NumPy arrays, to JAX data structures. And this all happens basically under the hood for you. And I thought I'd show you how you can switch to Pandas quickly and back, just so that you can sort of feel comfortable knowing that you don't have to sort of give up your favorite tools just to use this Datasets library. So the main thing that we need is there's a function called set format. And this will basically change the output format of our dataset from Apache Arrow, which are these dictionary type objects, to data frames if we use Pandas. And so once I've set the format, it's done in place. And then I can create a data frame by simply slicing over all of the elements in the training set. And so once I've got my data frame, I can then use my favorite Pandas function, which is to sample and just have a look at what some of these elements or these reviews look like. And so you can see here that we've got in the review body, some kind of summary or some customer review. And then we can see the number of stars associated with the review, as well as some metadata, for example, what type of product category we're talking about, and also the title. And so if we have a look at these, we can see, you know, in this case, this person is talking about a book that they're very happy with, and that they, you know, recommend it highly. So they've given it four stars. But then if we look at a negative one, you can see that this one says that, oh, the article never arrived, and I ordered it and I'm, you know, very unhappy, and that's why it's got 1 star. And so the goal, as I said, is we're going to take these review bodies and then we're going to try and predict the stars from them. So since we're still using Pandas, we can do quick kind of inspections of what kind of distributions we're dealing with. So one thing that's interesting to look at is like what kind of products we're dealing with. So we know that we have Amazon reviews, but the question is what kind of domains are we talking about? And so if we just do a value counts on the product category, we get a quick summary that tells us that home, wireless, and sports are kind of like the 3 most popular categories in this corpus. And what I'm going to do today is I'm going to train a model on just one of these subsets. And then using that, later you can choose to train on everything, or you can just pick another domain to see, you know, what the differences are in the model. And now that I'm running on Colab, one thing that Colab does, which is not always super nice, is they'll give you like a kind of not so great GPU. And if we look here with NVIDIA SMI, I'm using a Tesla K80. So it's a free GPU, but it's a pretty slow one. And so because of that, I'm going to pick a domain that doesn't have a huge number of examples, so we can train it in a reasonable time. So maybe what I'll do is I'll pick books, which has got around 5,000 examples. So the way that we can, we'll do this in a bit and show you how to filter it. But before we do that, I just want to sanity check how the distribution of stars look like. So we can see that it's a very balanced data set, which is what you often get in academic examples. Okay, so now that we've kind of gone through our data set and looked at some Pandas things, we need to kind of reset it back to Arrow so we can do efficient computations on it. So that's what the reset format function will do for us. And so now, like I was saying, let's pick one of these categories so we can train a model. And when I was running this last night, I had a better GPU on Colab. So I was able to run on the sports category, which you can see here has around 13,000 reviews. But with a K80, it's going to take maybe 20 minutes to half an hour to train. So instead, I'm going to pick something a little smaller. So we'll go with, as I said before, let's maybe go with books. which has around a third. So it should be faster. And so the way that we can filter in datasets is we need to use a function called dataset.filter. And then we just need to provide into this filter function some sort of logic which will tell us, which rows we should exclude or include. And so if we pick a product category and we say pick books, then what we can do is we can take the example that we get for every row, we look at the product category, and then we just check if it's true or false, if it matches the thing that we're interested in. So here I've got a function called filter for product, which will apply this kind of true, false Boolean logic to every row. And then in datasets, we can just apply a dot filter to our dataset object, and this will automatically apply to every split this filtering. So let me just run that quickly. And so you can see here, it's going through these 200,000 plus reviews. And
I think it's book, not books.
Thanks. That's the risk of live coding. Thank you. So it's going through all of the rows of these 200,000 rows, and it's applying this true false condition. And it's telling us, okay, that we've now got 4,927 reviews in the training set. And we can just check quickly that we have the same thing here. So it looks good. And the other thing that Datasets does, which is very useful, is it doesn't just cache the downloaded datasets, it actually caches every single computation you do. So you saw here, this computation was quite fast, it only took a few seconds, but sometimes you might have something which takes minutes or hours. But the cool thing that Dataset does is it actually caches the computation. So now if I run this again, it will say, we're loading the cached process data instead of having to recompute everything. And this for me as a sort of end user and developer has always been extremely helpful, because a lot of the time when you're doing machine learning projects, you're like running through a notebook and then maybe you blow up your GPU memory with your model. And so then you have to restart the notebook, and it would suck if you had to always keep recomputing all of these intermediate steps. And of course you could save them doing some manual stuff, but Datasets does it for you automatically, which is quite cool. Okay, so we've got now
quick question.
Yep.
So if you do like heavy processing, is there like a danger that you run out of memory if you do it like on a large data set?
Yeah, that's a great question. So Datasets, the Datasets library is based, as I mentioned, on this Apache Arrow framework. And this Apache Arrow framework gives you access to something called memory mapping, which allows you to basically process like humongous data sets, like hundreds of gigabytes, terabytes. As long as they fit on your hard drive, the library is able to process them basically on the fly, and it has a very low imprint or memory usage of your RAM. And so this means that, if I'm using, say, Pandas, and I download a 10 gigabyte data set, then the kind of rule of thumb that you may remember is that you need roughly, 5 times as much RAM as the size of the data set. So in this case, I might need like 50 gigabytes of RAM to process a 10 gigabyte data set in Pandas. But in the Datasets library, because it uses this memory mapping technique from Arrow, it means that you can just download this 10 gigabyte data set, and the actual RAM usage will be much smaller. It will be something like a few hundred megabytes. And this is a very powerful feature of the library. Okay, so we've now filtered the data set to just one of these domains. And just as a sanity check, we can just get a random sample. And in datasets, you can create random samples by chaining a shuffle function, which will just shuffle all of the elements, and then a select function, which will just take some set. So if we run that, we can see that now we've got all of our categories are book. And if we look at the reviews, yeah, someone talking about pages in the book. And this seems to be kind of as a sanity check looking good. Okay, so we've seen now how to filter data. And the next thing that we need to do is kind of do a bit of pre-processing on the labels, because in the current form, the labels are these star ratings, which go from 1 to 5. But most machine learning models, they kind of prefer if your targets or your labels go from 0 to n. It's just a kind of convention, but it's a convention that we sort of need to adhere to. And so what I'm going to do now is I'm going to take the star column, which has all the ratings, and I'm just going to shift them basically by 1. And the way that we do these kind of operations where we want to sort of transform the data is using what's called a map function in data sets. So the filter function was for kind of selecting and slicing the data, and the map function is for doing transformations on the data. So the first thing that we need to provide are some kind of label names. So here I've kind of transformed the star ratings from 1 to 5 into some actual human readable examples, which we can then use when we deploy the model. And here I'm just creating a dictionary which provides the relationship between the ID of the label to the name. And now we can define a function which we'll then use in the map. And what this function will do is it takes every row, you just feed one row of the data set, and it will shift them. It will shift the stars by 1, and then it will return a dictionary which contains the shifted label from 0 to 4, as well as the corresponding label name, so that then we can do some sort of human introspection later. So what you can see here, which was a bit different from the filter function, is that whenever you do map operations in data sets, you need to return a dictionary. And the reason for that is you might remember that when we were looking at the data set, if we just look at one of the elements, every row in a data set is represented as a dictionary. And so when we want to do operations on these rows, we need to also return a dictionary. And here, the keys of this dictionary will correspond to the new columns that we're going to create. And so at the end of this processing, we'll now have a new data set, which has the original columns plus these new ones. And so now we've got this function, we can just apply it with a map. And this is a very common function that we use in the datasets library to do all sorts of pre-processing. And if we apply this, it will crunch through these examples. And now you can see, if we look at the first element in the training set, that we've now added 2 new columns. We've got a label name column and a labels column, which is just shifted the star rating by 1. Cool, so that's been pretty fast. I hope it's clear, but if there's any questions, please feel free to interrupt. Okay, so that's more or less the basic pre-processing that we wanted to do just to get the kind of labels in the right place and to filter for a domain. The last thing I'm just going to do before we create a baseline is just create the inverse mapping of the label name to the label IDs so that we go from good to 3 and so on and so forth. We'll need this later when we want to tell our model how to relate the labels to names. Okay, so before we train a model, I think a really good practice in machine learning and in NLP is to create baselines. It's actually kind of surprising how often these baselines tell you something deep about your problem that you're trying to solve. So a very common thing can be that your data perhaps is actually very messy or noisy. And, if you invest a lot of time training, some super duper transformer, you may be wasting your time on all of that kind of hyperparameter search, blah, 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 when in the end of the day, you should just clean your data and improve it. So baselines are great to set the kind of expectation of how solvable the task is. And a lot of the time in NLP, you can use something like a naive Bayes classifier if you're doing text classification, or you might use, something like, I don't know, AdaBoost or something with some other sort of XGBoost type thing with some n-gram features. But today, what I want to use as a baseline is the zero-shot classification pipeline that Leandro showed us. And I like this as a baseline because it's very flexible. I can just tell it what labels I'm interested in, and it will then give me a rough idea of, how hard the problem is. Whereas if I do these other techniques, I have to actually train a model, and that takes a bit more time. So this is almost always like the first thing that I do in a project. And we're going to use the same model that Leandro showed us in his demo for the pipeline, which is it's a zero-shot classification model that was basically trained on 15 different languages. And so what this means is that we can provide our text in German, and it will also be able to hopefully provide some kind of classification of that text, even though many of these zero-shot models are in English only. So we just load the pipeline using the exact same thing that we did before in Leandro's talk. And the sort of only different thing I'm doing here is I'm specifying the device. So the pipelines can be run on CPU or GPU. And for a lot of inference, if you're just doing like kind of single request type predictions, then CPU is fine. But here we want to run over the full test set. So it's actually good if we run this on the GPU. And so basically, if device is greater than -1, this will put it on the GPU. But you have to be
warned. There has been a question concerning like the memory related stuff. Should one worry about memory when changing from Arrow to Pandas or others?
Yes, you should. So when we were converting our data set to Pandas, here, we first set the format, and this operation changes nothing on the dataset side. It just says, give me all my outputs as data frames. But then this operation here is creating an object called df in RAM, which has these things we mentioned. So when you convert to data frames, you have to be careful that you don't blow up your CPU. Okay, so we're going to create a zero-shot baseline, and if we just check how this works on some input text, I've got something like this: tennis racket is perfect. And the thing that we need to provide, as Leandro showed us, are some label names for the pipeline to understand. And so these label names are just these ones that I picked before. So we go from terrible, poor, okay, good, and great. And so if we run this on this example, we can see that the pipeline tells us that the highest confidence label is for great. And just as a sanity check, we could maybe change it to, did I do it right? If I change it to this is bad, then we can see that indeed the pipeline is able to distinguish between these two cases. Okay, so now we've got our pipeline. It's able to classify a single example. We now want to run this over the full validation set. And so again, we can use this map function to basically just apply the operation or the pipeline to every single row and then generate the predictions. And so what I've done here is I've created a function called compute zero-shot creds. And what this does is it takes the zero-shot pipeline, it feeds one of the rows to it, and with the label names, and this will generate the predictions, which will be precisely this dictionary here. So the predictions have labels, scores, and some sequence. And then what I'm going to do is I take those predictions and I'm going to convert them from the name, which is poor, terrible, okay, whatever, to an ID, which is the 0 to 4. So that's what I'm doing here. And then because we're doing map, where we're transforming the data, we need to make sure that the function returns a dictionary, which will have the column name that we're going to create, as well as the value that we get from that. And so then when we run the map function on our validation set, this will generate a new data set, which has these additional columns. And if we have a look at them, it will probably take, I don't know, maybe 30 seconds. do that. Let's see how we go. Can Colab handle this? Yeah, so you can see that running on a GPU is going to take us maybe 30 seconds. I think if you run this on a CPU, it probably takes you maybe 15 minutes. So you can see there's a big performance boost from doing things this way. Okay, great. And so you can see that we've now added a new column called zero-shot prediction. And so now the final thing, now that we've got predictions and we've got the ground truth, we need a way to compute some sort of metric around them. Oops. Let me just go down. Sorry about that. Colab has got a weird thing. Here we go. Okay. So just to sort of show you like what these predictions look like, if we look at the zero shot prediction, and we just look at a couple of elements. So here we're just getting the labels, like basically 0 to 4, where 0 is the worst and 4 is the best. And we want to compare this with the ground truth, which are these labels here. And so you can see here in these first 3 examples, the model got the first and the third one right, but it got the middle one wrong. And usually when you're doing text classification, you're probably familiar with like metrics like accuracy or F1 score and so on. But this is a kind of special data set because we're dealing with star ratings. And in the original paper from the creators of the data set, they make the observation that star ratings are ordinal. So they have a kind of an order from 0 to 4, so to speak. And so we should actually be penalizing like a 2-star prediction for a 5-star review more than a 4-star prediction for a 5-star review. And that kind of makes sense, right? Imagine that like the model is like predicting 4 stars and the true value is 5 stars. That's kind of closer to the true value than the 2-star prediction. And if we just used accuracy, we would kind of get a biased result because it would kind of evenly apply the same penalty across all stars. So we might think that the accuracy is bad, but the model is actually pretty good in the truth of distinguishing those cases. And so what they recommend is to use a metric called the mean absolute error. And this metric, you can see the description of it in the paper mathematically. Basically what it does is it just compares for every prediction, it compares the difference of that prediction from the true value. So if the star rating is 5 and the prediction is 4, you take the difference, you get 1. You then take the absolute value of that, which is why it's called mean absolute error. And then you divide it by the sum of all the total number of elements in your data set. So it's a very simple metric. And what it tells us is kind of like sort of like how far away are the predictions from the true values. And this notion of distance is kind of useful for this kind of task. And we could compute this ourselves in NumPy if we wanted to, but I'm lazy, so I'm going to do it in scikit-learn. So here we just import mean absolute error from scikit-learn. And then this function tells us that we need to provide the true values and the predictions. And so if we do that with the labels and the zero-shot predictions, we get something like 0.8. So a better, the lower the absolute error, the better the model. And so this is telling us that, for books, we're getting around 0.8. And now we've got something we can see if we can beat with our fine tuning. Maybe just a side note, because someone asked at some point, like, what is kind of happening in the zero-shot pipeline? I'll just take a minute just to explain that. So the way that the zero-shot pipeline works is it's actually adapting a task called natural language inference, where you've got a premise, a label, and a hypothesis. And the idea here is that in this task, you say, okay, a man inspects the uniform of a figure in some East Asian country. And the hypothesis is that the man is sleeping. And the model or the task is to predict if this is a contradiction, is it neutral, or does it entail the other? So does the kind of premise, does a hypothesis entail the premise? And so an example of that one is like a soccer game with multiple males playing, and the hypothesis, some men are playing sport. So that indeed says that, one entails the other. And then you can have neutral examples. And this is like a very kind of like academic type task where you're trying to say, given two inputs, does one entail the other or not? But it turns out that if you take this task, you can actually kind of hack it so that you can use it as a classification task. And so what Joe Davison did, he was one of the researchers at Huggingface. He, where is it? He adapted this task like this. So the idea is that you provide like a premise, like who are you voting for in like a question in 2020? The hypothesis is this text is about politics. And then the model, if it's trained on this inference task or this natural language inference task, it will then work out that the most likely label for this particular case is politics. So it's a great way of kind of inferring what kind of are the most likely labels, which is a way of kind of adapting to text classification. And if you want to know more about what's going on there, I'll just chuck this blog in the chat. It's a great blog and worth reading. But that's the zero shot. So let's now look at training a model. So the first thing that we need to do to train a model is take all of these reviews, which are kind of raw text, and convert them into a numerical representation that we can do matrix operations on, because at the end of the day, all of deep learning is basically matrix operations. And the technique that we use in NLP for doing this is tokenization. So Leandro kind of mentioned this a bit, where he showed in the pipeline for, I think, named entity recognition, that the sentence was getting kind of split into subwords or into words and into smaller things called subwords. And these atomic entities are what we call tokens in NLP. And the idea is that these tokens can then be like mapped to a vector or an embedding vector. And then these embedding vectors are the inputs to the model, which then we do attention and all the other stuff on top of it. So I'm not going to go into like tons of detail about like how tokenization algorithms work, but if you're interested, you can watch this video from Lissandra, where he explains kind of at a high level how this really is put together.
There was a there was a question from Ashish concerning that, and he was asking like, what happens to emojis?
Great. So there's a very important thing to mention here, which is that some or many of the most popular tokenization algorithms, they kind of rely on some rules to figure out how do you split, like say, a sentence into these tokens. And those rules have some sort of, like say, implicit bias about how you should do that. So for example, there's an algorithm called word piece, which is quite commonly used for BERT and other models. And this model, or this tokenization algorithm, is great for like languages like English, which have kind of white space between them. So you can easily sort of figure out the boundaries of words and then figure out how to chunk that into subwords. But there are languages like Japanese, which are character-based, and they don't have a concept of white space to differentiate between the individual, say, words. And emojis are kind of in this category where they're not really a word, but they're more of a character. And so if your application really needs to have emojis in its vocabulary, then what you'll probably need to do is train a tokenizer with these like algorithms to figure out how to kind of learn that emojis are a frequent token that should be represented, because that's more at a character level. There are some other techniques you could do to just sort of add them to an existing tokenizer, but I think I'll skip that for now, unless Leandro has a secret trick for dealing with emojis.
No. I mean, there has been another question, which is, how can you adapt a zero-shot learning baseline for a multi-label task?
Good question. So as far as I know, Let me think about it.
I mean, I know the answer to that one, so maybe I can answer.
Okay, great.
In the pipeline, there's a flag that you can set, which is multi-label equals true. And if you set it to true, then instead of normalizing the output scores to be to 1, it doesn't do it. And so you can set like an arbitrary threshold. You can put that in the chat.
Awesome, thanks. Okay, cool. So we're going to load a tokenizer. And one thing that's important to know is that the tokenizer, for every pre-trained model, you have some weights, which is what Leandro mentioned. But you also have a corresponding tokenizer that was used to tokenize the corpus or the data set for the pre-training. And it's always really important that you use the same tokenizer with the same weights, because there's a strong connection between like how you kind of feed the correct inputs into the model with the right tokenization scheme. So here we're going to use a model called XLM Roberta Base. This is a model Leandro mentioned, which is fantastic for multilingual applications because it's been trained on 100 different languages. And so as long as your languages are part of that, then there's a good chance that you can generalize across more than one language at once. And the way that we kind of create our tokenizer is by using this from pretrained method. And there's an auto tokenizer class, which will figure out automatically for you what type of transformer you're using just based on the checkpoint name. So if we run this, this will load the tokenizer from the hub. And this is just downloading some configuration files. And we can look at some attributes of this tokenizer. So for example, it has a vocabulary size of 250,000 tokens, which is actually much larger than BERT because it's a multilingual tokenizer. So it has to sort of adapt and handle things like Japanese, Chinese, but also English and German. The other thing that...
Just as a heads up, like we have about 20 minutes left.
Okay, cool. So I think I'll then sort of skip some of these like technical details and then just skip to the application parts. Okay, so if we want to tokenize text, we just feed in a string like this. And this will then produce two kind of outputs. Here you can see the input IDs, which are basically these numbers that represent each token. And then there's an attention mask, which we don't really need to worry about today, but it's something that is used to indicate to the model which tokens it should ignore or include in self-attention. So if we like decode these inputs, then we get, we can see the relationship between the token ID and the corresponding token. So here you can see gut and tag, my name is Louis. And these kind of tokens like an S and a /S, they're special tokens that are used to indicate the start and end of a sentence. And, you know, we don't really need to use them today, but they're just worth knowing about. Okay, so now we want to tokenize all of the reviews in our data set. So we do the same trick that we did before, which is that we just create a map function. And for our map function, we just need to give it some logic that will say, just tokenize the data. And so here we're going to take a tokenizer, we're going to feed it the review body. And I'm also using truncation to basically, if the review is longer than a certain number of tokens, I'm just going to contract it and just chop everything and throw the rest away. And in the paper, they recommend setting a truncation length of 180 tokens. So I'm going to do the same thing. And so now if we apply this, it's going to power through the data set and create these new columns of these input IDs that we can then use as inputs to our model. And one thing to mention is that the tokenizers here are very fast. They're actually bindings, Python bindings on Rust. And Rust is extremely high performance computing language, kind of like C++, but you know, a little bit safer on the memory. So this is really fast. And if you have a lot of CPU cores, it will go even faster. Okay, so now if we just have a quick look at one of the elements, we can see that we've got these input IDs like this. And these are the numbers that we're going to feed into our model to do the training. So to train a model, we just need to load one. And again, the task that we're interested in is text classification, which falls under the general task of sequence classification because we've got a sequence of tokens. So we can use this auto model class and the from pretrained method. And we just have to provide the checkpoint, which is where it's located on the hub, the number of labels that we're dealing with, which is 5 in this case. And we also provide the mappings between the label numbers to the names and back so that the model can then automatically produce this for us when we do inference. So if we load this model, it will download it from the hub. And you can see that Roberto is relatively big. It's around 1 gigabyte model, and it will take probably 30 seconds on Colab. But again, as Leandro mentioned, these will all be cached into your cache folder. So this kind of waiting step is usually only done once. So let's see how this is going. Okay. Okay, great. So you're going to see most of the time a warning like this, which will say some weights were not used when initializing the model. And all this is telling us is that we've got a pre-trained model, which has some weights in the body, and we've attached a head, which is essentially a fully connected network with randomly initialized weights. And these are the weights that we need to fine tune. So these warnings are normal and expected. And so now to train that model or to do fine tuning, you could do this in raw PyTorch or raw TensorFlow if you wanted, but the Transformers library provides a trainer class, and this basically wraps all of that logic of looping over the batches of the data loader and stuff, and just you just have to pass the data set and it will take care of it. So the main thing we need for the trainer are some training arguments which specify the hyperparameters, and we need to provide a metrics function so that we can do evaluation during training, and along with the data sets that we want to train and evaluate on. So if we start with the training arguments, this class takes a bunch of inputs. The most important one is the output directory. This is basically where we're going to save the model, all the checkpoints of the model and all of the information about the tokenizer. And everything else after that is completely configurable. So here I'm saying let's evaluate at every epoch. I'm specifying the learning rate, some weight decay, and the number of training epochs. I'm just going to train for 2 because it's a relatively small data set, and this will probably start overfitting after that. And the other thing that's kind of interesting is I'm adding a push to hub argument, and this will ensure that when the model is trained, that then we can just push it to the hub automatically without having to do any logins. So let's see, this is done. And now we need a metrics function. So we already have this mean absolute error from scikit-learn. And the only thing we need to do is just wrap this in a dictionary so that we can return the metric during training. So that's what I'm doing here. I'm just using the argmax to get the most likely candidate. And then that's it. We just now need to instantiate the trainer. The trainer receives the model that we want to train, the arguments, the training data sets, and the compute metrics. And if we provide the tokenizer, like I do here, this will, okay, I need to log in. So let's do this login. Okay.
While you log in, there was a question from Noah about how would you fine-tune a model using your own CSV example?
Great question. So one way to do that would be to load your data set. Like you could do something like load data set, and then you can use a CSV loading script. And then you just need to provide an argument called data files, which would be like, your train and then your like path to data.csv. And this will create a data set for you, a data set object of your own CSV files. And this also can be done for JSON and for Parquet or for other formats. that's probably the best way to get started. Maybe Leandro, you can put a link to the loading functionality of the datasets library.
Yeah, will do. Another question was about if we show SageMaker today, and I think there's a dedicated workshop for SageMaker at some point in the near future, and I'll just put the link to that because I think we don't have time to go into details.
Great. Okay, so I've just logged in because I forgot to do that before, and I'm going to specify my training arguments. Okay, so now the trainer. Okay, so what's happening now is we specified the output directory, but because we specified push to hub, it's creating a repository for us on the Hugging Face hub under my account. And this repository is empty at the moment. Basically, there's nothing in it. And we're going to now train the model and then push all of the weights to the hub automatically. So if we just do trainer.train, this is now taking the books subset that we specified, and it's now going to train for 2 epochs with these parameters we picked. And you can see here, it's going to take around 8 minutes or so. So while that's training, I'll show you something I prepared earlier in the oven. So what we're going to get at the end of the day is something, let's see, where would it be? So we're going to get a model like this. And what the trainer will do is it will automatically fill out the model card for us. It will tell us what the loss was, what the metric score was. And you can see that this model got a metric score of around 0.48, which is roughly half the error that we saw in the zero-shot classifier. So this has definitely gotten much better. And we can also provide in here, like, I love this tennis racket or whatever. And in this widget, we can then compute the inputs, and this will automatically provide the inference and the labels for that prediction. And the cool thing is that we can write in different language. So maybe dieses, I don't know, Buch. And you can see that it's also worked out, how to do it in German. And I don't know, I don't know any French, but I could say me encanta este libro in Spanish. And you can see that it's also able to differentiate between these different languages, which is quite cool. So while this is training, I want to show you what would be the natural next step. So we've now got a model that is on the hub, and we would now like to maybe interact with this model somehow. So there's a third notebook I will show you in the last 5 minutes. So I'll put this in the chat. So there's a library called Gradio, which is really cool for doing demos of machine learning models. And so to kind of give you a taste of what that looks like, I'll just install these dependencies. So you've got a model, you've got some weights, but you want to share this with your colleagues at work, or your pets, or your family. And the usual way that you have to do this is you need to write some sort of web application in Flask or in Fast API, and you have to kind of do this annoying stuff with building endpoints and then deploying the model itself. And this Gradio library lets you do that basically in your notebook, and then I'll show you how we can deploy it. So here I've got this model that I trained last night, but it's basically the same one that we're doing now. And so if we download this model, we can then have a pipeline just like we saw before. And then what Gradio provides is something called an interface, where you tell it, how should my predictions look like essentially, how should I format my predictions? And then you provide some inputs for the user and some sort of outputs to sort of understand what the label and scores are. So hopefully this downloads pretty quickly. Okay, and so what I thought would be kind of fun is that instead of just predicting the word like terrible, poor, okay, I created some sort of mapping so that we get, happy cats or sad cats, or in the worst case, a bit of poo if the review is bad. And if we then run this predict function, it will process these inputs and then it'll give us an emoji instead of the word. And so now when I run Gradio, it's going to take this pipeline and it's going to provide me with an interface like this, where I can now input some text and see what the predictions are like. So if I input, I love these running shoes, and I hit submit, it automatically gives me the label, but I can also do this in French, and it also will give me some prediction. And you can also type in here anything we want. So Gradio has given us in more or less like, this is just one line of code, basically 2 lines of code to launch it, a fully working web application. But this is only running on Colab. And what we want to do is we want to share this with people somewhere where it's going to live permanently. And so if we go to Huggingface and then we go to resources and spaces, this is where we host all of these interactive demos. And so if you want to create a new space, you basically go to your profile, you hit new space, and I'm going to call this like, I don't know, Amazon reviews demo. And you can select either to create a Streamlit app or a Gradio app. And Streamlit's also really great if you want to make kind of advanced data applications, but Gradio is great for just simple machine learning demos. And we're going to specify that it's public, so we can share it. And so this now has nothing in it. It's like a Git repository. But if we go to files and versions, we can now add some files. So I'm going to create a new file where I'm going to put the logic of my application. So I'm going to call this app.py, and I'm going to take my my Gradio logic here, where basically I provide the imports, and I'm going to provide the pipeline, and I just provide this predict function. And then we just provide the Gradio interface. And like that. This should work, I think. Yep. Okay, so we've got the imports, we've got the pipeline, we've got the mapping, we've got the predict function, and we've got the Gradio interface. So I'm just going to commit this file. And the space will be automatically built by the backend. And you can see we've got an error. So if we click on what the error is, it says we don't have transformers. So you can see down here that we can add a requirements file. And so let's just do that quickly. Let's add the dependencies of the project. So let's add transformers and the sentence piece library. Oops. We add that. So this will now automatically build both the installation of these dependencies and the Gradio application. And it might take some minutes while it's building. So while that's happening, let's just go back and see if our training is done. Okay, so you can see that we've got a couple of minutes left, but already after just one epoch, we've managed to almost halve the error that we were dealing with compared to our zero-shot pipeline. And this, I think, gets to an interesting question, which is like kind of how many samples do I usually need to get good performance? And for text classification, Leandro and I have typically found that, often with something as little as 50 samples, you can actually get pretty good performance because the transfer learning from the pre-trained model is so good. As long as the domain is not super different and as long as you don't have hundreds of labels, this is often going to give you very good results. Okay, so that's still got some time to run. Okay, so now let's see, what am I running into now? I missed PyTorch. So this is the problem with hacking live. Yeah, you pay the price. Okay, so I'm just going to add PyTorch to the dependencies. And so it will build again. But yeah, if there's any sort of questions at this stage, I could answer them.
Somebody, Ben, asked about partnership with GraphCore and if we can tell anything about the experience with their accelerator.
I'm not very familiar with the details of this, but I think we had recently a blog post about the partnership. So I'll put this here in the chat. And I think here there's some information about like what kind of speed up and differences you get. So just for people who are asking, I think GraphCore is a company that is creating a kind of custom chip for deep learning applications. And it's quite different to say a GPU from what I understand in architecture because it's built around graph data structures. And I think here you can see, like in their comparisons, what they're seeing in terms of like throughput compared to like a DGX workstation. So it seems quite impressive. But as far as the experience of the collaboration, I don't know the details of that. Okay, so let's see what's happening here. Don't tell me that. Okay, great, it worked. So, so now we've got this this application running on the hub, and I'll just chuck the link in the chat. And you can see here that I can type in some text like, I really enjoyed wearing this jacket in the rain. And if we submit this, it's giving us now the prediction of the emoji and the score. And so just to give you like a very fast taste, this was roughly, I don't know, 5 minutes, maybe 10 minutes with some debugging to get this running. But this, at least for me, is much, much faster than doing things, manually with Flask or Fast API. So if you're interested, you can sign up to the Spaces beta that we provided in the chat, and you can already start playing with Gradio and Streamlit with the models in the hub. Okay, so let's see, this model is finished. So we're now getting around 0.48 like we saw before, which is great. And so then the last thing we need to do is just to push all of the checkpoints to the hub. So if we push this model, it will now push everything that we have to this repository. So at the moment, there's nothing in the repository, and these models will be pushed. And you can see when we do this, it's like saving all of the checkpoints into this output directory along with the tokenizer, and then it will push everything very quickly there. Let's see, this might take a while because Colab, I think, doesn't have the greatest bandwidth, and XLM Roberta is quite big. So I think, for now, this might be a reasonable place to stop. And if there's any questions to wrap up, there's also some additional details in the notebook you can look about how to evaluate cross-lingual transfer. But I realize that I'm already 5 minutes over, so I'll stop now.